Good day to all. Today we are going to see about that static resistance control. From the word itself, you will know this is the resistance control and how it will occur that we will going to see here. See here the three-phase supply is given to this induction motor. This induction motor will connected with the diode rectifier. What is that meaning of rectifier? It converts the AC voltage to DC voltage. The main purpose of using the rectifier is to convert the AC to DC. If it is inverter, that will connect it to DC to AC. That we know already. Here, you'll see this induction motor will connect it to the diode rectifier. This diode rectifier will convert this current into DC current. Then it will connected with that inductor. Here inductor will have storage of this DC. The current flow over here is a ID. Then it will connected to this switch, and it will connected across over the resistance. Here this resistance will have a change because of this switches. If the switches, the resistance, or we can say this as a load. So if you are changing, or if you are changes in that switches, the load will also change. So this is the static resistance control. According to changes in these switches, we will have the changes in that load. If you are seeing the waveform, see over here, the certain time of that ID, it will have a 120 phase shift over here. Then it will have a 0 value. There is no pulses over here for that pi. After that pi also, the negative sign will also come. Then we'll have a no power over here. Then it will have a 2 pi. This is the waveform of current to speed. Then this is the rotor current waveform of this static rotor control. The conventional method for variation of rotor resistance was done by a variable rheostat in the series of three-phase winding motor. This method of the control faced a problem, and this was not economically viable. As I said before, this method speed control faced more problems. See here, if it is switches, some error will be also occur, so it will have a more problem. So in solution to this problem, thyristor is used to, which is connected across the enable external resistance, and effective resistance is varied simultaneously. Then the effective value of resistance across the terminal A and B, that is RAB, is varied by varying a duty cycle of transistor TT, which is then varies the resistance of the rotor circuit inductance. So is added to the circuit to reduce the ripple and discontinuity in the DC link current ID. So the rotor current waveform shown in when it is ripple, if it is neglected. So if it is ripple, it is neglected. Why we are using this TR over here? Because there is some loss of energy over here. So we are using this TR here in the static resistance control. That is we are saying here, if it is effective value of resistance across the terminal A and B, that is RAB is varied varying a duty cycle of the transistor TR. So the rotor current waveform is the ripple when it's get regulated. When the ripple is occur, it will be neglected. Thus the RMS value of the current will be IR equal to root 3 root 2 by 3 into ID, the resistance between A and B. See, you can see here the resistance between A and B terminal will be 0 when the resistor is on, and it will be R when it is off. So the voltage value between the resistors terminals is given by RAB into RAB is equal to 1 minus sigma R. The main thing is, if the resistance between A and B terminal will be 0 when the resistor is on, otherwise it will be R. So that's why we see here RAB equal to 1 minus sigma into R, where sigma is a duty ratio of the transistor. Then therefore the total rotor resistance is varied RR to 0.5 into 1 minus sigma into R, as sigma is varied from 1 to 0. The electrical power consumed by the REAB resistor per phase is power consumed per phase equal to BAP divided by 3 equal to 0.5 into 1 minus sigma into IR to the power of squared. Then we will move up to that switched reluctance motor. What is that switched reluctance motor? We can simply say that's the SRM. It is a type of stepper motor and electrical motor that runs the reluctance by a torque. Unlikely common DC motors types, power is delivered to windings in the stator case. So his greatly simplifies the mechanical design, as power does not have to be delivered to a moving part, but it complicates the electrical design, as sort of switching and system needs to be used to deliver the power to the different wing stators case rather than the rotor. Then this is greatly simplifies mechanical design, as power does not have to deliver the moving part. Here this is the main thing, the power does not have to deliver the moving part. Why? It is because that simplifies the mechanical design. But the thing is, it is complicates the electrical design, as some of sort of switching systems need to be used to deliver the power of different windings. This is the main thing, it is used for different windings. And with modern electric devices, preciously timed switching is not a problem, but the SRM switch reluctance motor is popular design for a modern stepper motors. Its main drawback is a torque is ripple. Here the torque of this motor will ripple. That is the main disadvantage of this SRM, which means a switch reluctance motor will have a torque is ripple. Then the switch reluctance motor have wound field coils in a DC motor for stator winding. It has a wound field coils in that stator section, that is a stator windings. Then rotor however has no magnets or coil is attached. In this stator it has a coil, but in that rotor there is a no coil. In that rotor there is a no coil. Okay, it is solid state pole rotor having projecting a magnetic poles, and which is made up of a soft magnetic material, often laminated steel. When the power is applied to this stator windings, the rotor magnetic reluctance creates a force that attempts to align the rotor pole with the nearest stator pole. And that's why I mentioned over here in different colors when the power is applied to the stator windings. The rotor magnetic reluctance creates a force. When if you are apply the power to the stator windings, when the rotor magnetic reluctance creates a force to attempt the rotor pole to with the nearest stator pole. Then in order to maintain the rotation of the electronic control system, switches on these windings of successive stator poles. So this magnetic field is stator leads to the rotor pole, which is pulling it forward. Rather than using this troublesome high maintenance, the mechanical commutator to switch windings current in traditional motors, the switch reluctance motor uses a electronic position sensor, which is used to determine the angle of the rotor shaft and the solid state electronics to switch the stator windings, which also offers the opportunity for a dynamic control pulses, timing and shaping. Thank you.